So just to confirm, we're being recorded right now? Everything's set up for that? Excellent. Um, well, thanks so much for the organizers. Thanks to all of you for being here. This is actually my fourth time visiting Florence and my second time giving winter school lectures. The first time I gave lectures here was on QCD and collider physics, and some of those themes will be infecting this talk today about machine learning. Let me first make some general advice to you, which is to take advantage of the time that you're here for the summer school. Take advantage years you're going to see for the rest of your professional careers. So you'll make wonderful physics friends here. Engage with your lecturers, both myself and Nathaniel, not to speak for the lecturers later in the week. We love engaging with junior researchers, so please take advantage of our time and this beautiful city. Gotten your exercise for the day, walking up the hill, and take advantage of this to get more exercise, seeing this absolutely amazing historical place. So when I was your age, I made the mistake of not going to a school like this. You've already done one better than me by being here today. I find it a lot of fun to give these type of lectures, both because I get to engage with the next generation of theoretical physicists, but also it gives me a chance to try to consolidate my understanding of the field that I work in. And the particular field that I'm excited about at the moment is machine learning for fundamental physics. And this is a particularly challenging talk to give on the blackboard. And I am not going to have any slides. There will be slides for the public lecture this evening, so I'll allow myself to show pretty pictures this evening. But I'm going to try to do this all in equations, which means that we're going to be focusing on the conceptual aspects of things and not on the coding aspects. And I myself am not a particularly good coder. So I rely on my collaborators, mostly junior collaborators, if I want to do anything that's production grade. But right now I'm actually on sabbatical. So this is kind of fun for me. I'm on sabbatical. Living in Paris, splitting my time between IPHT and IHES, and on sabbatical, I'm trying to be a little bit of a grad student again. And let me just mention that I'm trying to figure out how to apply AI to my research in new ways. And so two things that are on my mind. So if you see me around, I'm furiously on my laptop. That's because I'm working on new optimization algorithms, but trying to use them to solve theory problems. And by theory problems, I really mean like hep-TH theory problems. So I've been fascinated by the modular bootstrap. And this is something that I never thought that I'd get involved in, but I'm trying to use new types of AI optimization strategies to try to gain insights into two-dimensional conformal field theories. So that's one thing I'm doing. And then the other thing that I'm doing is I'm trying to figure out how do you actually use chatbots for theory insights. And some of you may have seen my colleague at IFI, Matt Schwartz. He put out a paper on the archive where he claims that Claude helped him write it, or in fact, I think he claims that Claude entirely wrote it. And I have not been as successful as Matt in that endeavor. I have found that working with a chatbot has stretched my brain in exciting ways, but also frustrated me in less exciting ways. But it's actually been really interesting to engage with an AI agent, trying to think of the AI agent kind of like either a grad student or a collaborator. And even though it itself has not come up with any proofs that have been valid for my research, it has actually inspired me to come up with valid proofs, and it's exposed me to aspects of the literature that I hadn't seen before. And I'll mention a little bit on Friday, kind of the ways that maybe we as theoretical physicists, how our lives and careers might change in response to some of these AI tools. Now, I should say that these two things are very different ends of the spectrum of what you're doing with AI. Here, I'm taking it's like numerical optimization strategies. You don't even have to use the word AI. You can just say I'm doing numerical optimization. I'm not even using AI tools. I'm doing everything in Mathematica. But here, this is really this kind of brave new world that comes about when you have computational systems that exhibit something that mirrors something like human intelligence. And but the thing that I want to emphasize in these lectures a bit is that AI, machine learning and even, represents a giant and growing spectrum of techniques across mathematics, statistics, computation, data science. And so like on the one end of the spectrum, we have things like basic linear regression, which is kind of one simple extreme of what you could mean when you're thinking about doing AI ML. And then there's the other end of the spectrum, which maybe gets more headlines, where you can imagine having your embodied AI overlords, where you can imagine like having lectures of this, maybe not in 2027, but let's say 2028, that you'd have a robot, giving lectures, inspiring you, and that could happen. It's not even that crazy. And there's a lot of different strategies in the middle here. And yet, all of these strategies remarkably share at some level the same philosophical, or if not philosophical, at least kind of technical or computational underpinning, that what these all are optimization in response to data. And it just happens to be that the notion of data is a lot bigger than I had ever thought it would be. That I thought of data as being like experimental data, data that you collect from an experiment. My world of collider physics, thinking about all the data you collect from the Large Hadron Collider. But data is also theoretical data. The set of all Feynman diagrams that you can draw with certain types of interactions. That's a type of data. Then there's conceptual data. Some of the ideas, for example, that Nathaniel might talk about this afternoon, like this is data where there's kind of knowledge graphs involved. And remarkably, all these different formats of data, when optimization is applied to them, end up giving you quite powerful computational systems. And again, in ways that we may not even fully appreciate what they can do. And I'll try to, in these lectures, tell you at least some aspects of what this can do for fundamental physics. So this will be my working definition of machine learning for these lectures. Optimization in response to data, which it actually turns out to be a rather broad umbrella, though I'll only get a chance to scratch the surface in these lectures this week. So the title of these lectures are Machine Learning for Fundamental Physics, which is a little bit of an ambitious title. I myself work on collider physics, so a lot of the examples will come from my own research domain. But a lot of what I say is equally relevant, for example, for cosmology, which is also another aspect of fundamental physics, though there are key differences that would be fun to talk with you about it. But the word fundamental is actually essential here, because there's kind of a key assumption. And I would say that this key assumption is what distinguishes studying of fundamental sciences versus studying other things like applications of science or studying emergent properties of systems, where the assumption is that there really is an underlying model of the universe. And moreover, that not only is there an underlying model of the universe, but our goal should be to try to understand that underlying model of the universe. And that the data that we see, so not only is there a model of the universe, but that model of the universe generates data. And the data that we see can be readily derived, or at least approximately derived, from that model. So we assume that there's some probability for seeing some set of data. Again, this could be experimental data, theoretical data, concepts. Okay, but there's some probability of seeing data given, so this vertical line means given, some underlying theoretical model. And we assume that this exists, and we assume that we, to some extent, have access to it. If we don't have access to this, if we don't have some sense of, I hand you a model, if you can't generate me data from that model, then nothing that I say in these lectures is going to be relevant. I really need this to exist, or at least I need to appreciate that such a thing could exist. And so then if you say, what does success mean in this context? Success, if you're trying to infer the underlying dynamics of the universe, success means that your data is likely, I'll put this in scare quotes, likely given your model, where we'll have to argue what does it mean for things to be likely. Um, but data by itself doesn't necessarily have intrinsic value in this area. It's really your ability to come up with an explanatory model, and then we can argue about ourselves to what extent something's explanatory, to what extent I might have prior knowledge that could inform that model, use concepts like Occam's razor to decide which models I favor versus not. And so there's definitely a human subjective criteria going into this word likely. But this is really where we have a kind of a starting point. And maybe just one kind of other kind of philosophical thing to say is that the type of science that I'm talking about, which generally I would just call curiosity-driven research, that curiosity-driven research is really a quest for human understanding. And so, I don't care if the AI understands theoretical physics. I want to understand it. And so some of the things that we'll talk about will be ways of constructing AI systems such that the answer that they give you are ones where you as a human can interpret it. Okay. So now to make this a little bit more concrete, not only do I going to assume that there's some generating model, that there's a probability for data given a model, but I assume that I really have something like that in hand, that is, I can faithfully make a simulation of the data generating process. So let's focus on the case where the model is, for example, the standard model of particle physics or lambda CDM cosmology. And then I want to understand the data set that I might get from the Large Hadron Collider, or the data set that I might analyze at the Rubin Observatory. And I imagine that I can make a faithful simulation of what data might look like. So we're going to assume that such a thing exists. So we have some good numerical estimate or some sampled estimate of this P of data given model. And under that, the banner, in fact, another perfectly fine title for this lecture series could have been, we're going to be doing simulation-based inference. Where, again, assuming that I have an underlying model and that I have an ability to some accuracy to simulate what synthetic data might look like, then given real data, I then want to infer what the underlying model is. That's going to be the framework that we're going to be working in. So there's a couple of aspects of this that I just want to emphasize. One is that machine learning is optimization in response to data. I need to have some source of data, and I'm going to assume that I have a source of data, simulated data, from the fact that I can simulate through some program. I could simulate the universe through an n-body simulation, or I could use a parton shower event generator to generate synthetic collisions. I assume that I have that. And then the fundamental physics aspect is that given experimental data, I want to be able to infer what the underlying description of the universe is. And that's the cycle that we're going to be exploring in this lecture. And I would say kind of arguably, no matter what field you're working in, even if you're working with theoretical data and you're studying, for example, scattering amplitudes, you're going to hear things about S matrices in later weeks, that at some level, I'd argue that this is the core of what it means to do machine learning for fundamental physics, that you're trying to figure out what the underlying rules are, and that's what success looks like, is coming up with underlying models or principles to explain whatever you're seeing. Now, as an aside, and this is not what I'll be talking about in these lectures, there's another really exciting area where you're actually using physics to understand AI systems. That as you actually use your toolbox from theoretical physics, you use your understanding of quantum many-body systems or your understanding of quantum field theory to understand or try to gain insights into the way that AI systems themselves work. I'm not going to be talking about that at all in these lectures. But that's another thing. So in the one hand, we're going to use AI for fundamental physics or machine learning for fundamental physics, but there's also a growing community of people who are using fundamental physics to gain insights into the way that machine learning works. Okay, so just to summarize the kind of overarching goal of this week, at least for my lectures, assuming that you can simulate a range of possible universes, how can you use machine learning, optimization response to data, how can you use machine learning to figure out which one of those is likely ours? And this turns out to be a very rich subject. I'll only scratch the surface of it. And you should take advantage of the fact that I'm doing this on the Blackboard to ask questions that you might have about this. And in fact, to put my money where my mouth is, let me just pause to see if there's any questions at this outset for this general framing before I give you a little bit more of an outline of where we're going to be going for the rest of these lectures. Yes?
Maybe it's too early to ask this question, but for what I have in mind, this kind of process is like finding a minimum of some curve. And my question is, usually when we do physics, it's like, sampling this distribution, not continuously. While this model, you move a little bit and a bit. What tells us that we don't get stuck in some false minimum in this procedure? Maybe
Yeah.
where to ask this question, but
yeah.
my fear is that doing that, maybe you end up in a minimum which is not the real theory, but just
Yep.
something.
So let me translate the question. So the question is, if I'm doing some type of optimization, I'm imagining optimizing some continuous function. And if I'm doing simulations, oftentimes I only get discrete samples. So given discrete sampling, how can I make sure that I actually have a good continuous estimate? And if I don't have a good continuous estimate, that might mean I might get trapped in local minima, right? That's basically right. And so the problem is just even worse than what you just said. Like it's even harder than that thing that you're imagining. You're imagining that the translation from discrete to continuous is part of the problem. I mean, it is part of the problem, but it's even worse than that. That is, there's like genuine local minima structure. There is no way with optimization to guarantee through that you found the minimum, unless you can prove that it's a convex optimization problem. That we are dealing with a very complicated system for which we have very few theoretical guarantees. And some of the work that's going on in the more physics for AI direction is actually trying to establish under what circumstances you actually have certain theoretical guarantees. But a lot of what we're doing is heuristic. And it means that, well, it's following in the grand tradition of what we do as theoretical physicists, right? As theoretical physicists, we oftentimes build systems that are not exactly mathematically rigorous. We got a sense that this is roughly how it works, and then you wait a couple decades and the mathematicians formalize everything for you. But that's roughly where we are right now, and then you have to decide your level of comfort with these things. But there are certain cases where even in the presence of a provable guarantee, you still get the wrong answer because eventually you have to put it on a computer. And then there's issues that happen when you have round off errors and things like that. So it's a good thing to mention, but that's that's only a small part of the problem. This is a very hard challenge to do in generality. Yeah. Yes.
How bad does it get for discrete to discontinuous when there's stuff like phase transitions?
Yeah.
How does so he asked about the false minimum.
Yeah.
How does this help get phase transition point at discontinuity?
Right. So the question was, does the translation from discrete to continuous, does that have any implications, for example, for phase transitions and such? And the answer is yes, and it's complicated. So, for example, you can show that as you make different choices about how you do your machine learning, the actual learning itself undergoes different phase structures. And the way that the learning proceeds depends on various choices that you've made in setting up your problem. And you can actually make phase diagrams of the learning behavior and actually show that in certain cases it behaves the way that you want, in certain cases it doesn't. And it becomes that's the reason why this is such a rich area, is that actually the learning dynamics are as complicated as physical systems that we've encountered in the real world. Yeah. And yet we're going to try to learn something about the universe doing this. Okay, so let me just tell you what these 5 lectures are going to be about, roughly speaking. So the rest of this lecture, I'll call it lecture 1, the rise of centaur science. So I'll actually be showing a cartoon at the public lecture this evening, maybe emphasizing more about why I'm invoking the mythological creature of the centaur to talk about machine learning and fundamental physics. But roughly speaking, just talk even in more general terms about how we can teach machines to think like a physicist and how physicists can learn to think like a machine. And this will be kind of a link into the public lecture that I'll give this evening. And then the kind of meat of the lectures will be lectures 2 and 3. So lecture 2 is about machine learning through the lens of physics. And the goal of this second lecture is to actually show you that a bunch of the machine learning jargon that you might have heard, we can translate that into physics jargon. And that certain things that might seem mysterious to you about machine learning are actually things that you're super familiar with, including like classical mechanics. And so like things like the Euler-Lagrange equations or things like Newton's laws, like those actually show up in machine learning systems, so maybe not with that language. The third lecture, I'm punningly calling frequentistly asked questions. That if you're trying to infer the underlying structure of the universe, you have to decide what statistical framing you want to do. And the 2 common framings are Bayesian inference and frequentist inference. And I'm not going to necessarily take sides in that debate, but I want to just show you kind of why is it that when you're using machine learning, you actually have to think about the statistical paradigms that you're using for making your inference. And I would say that the meat of these lectures are in these 2 things. And so if you can come away with an understanding of how machine learning jargon is actually physics jargon in disguise, and some better understanding of inference and uncertainties, then I've done my job. Then we can have some fun. Both myself and Nathaniel are enthusiasts about optimal transport, and that's a branch of machine learning that I'll try to tell you a little bit about. A lecture about jets in space. And then going on to full speculation mode, talking about just the future of AI plus physics, and giving you some guesses about where things are going, about possible trends, and that will give me a chance for me to explain some of the things that are going on in the field and give you my opinions about it. That's where we're going to be going for the rest of this week. Okay, so we'll start off with the rise of centaur science. And let me not give away the joke that you'll see in the public lecture this evening, but just to say the mythological creature, the centaur, is half human, half beast. You can ask which side is the more physics side of that equation versus which is the more AI side of that equation. But you'll see an interesting cartoon smash up at the Spritz of Science tonight. So why is it important to balance, right, physics insights or physics intelligence with machine intelligence? Why is that even an issue? Sometimes when we think about fundamental physics, we say, oh, the challenge of fundamental physics is that we have a big data problem. And big data is one aspect of why incorporating machine learning strategies into our fields is a good idea. If you're having collisions happening at the Large Hadron Collider every 25 nanoseconds, yeah, that's a monstrous amount of data. Cosmological surveys are generating so much data you can't even kind of keep it in your head that you have to do more statistical strategies on it. Even fields like gravitational wave astrophysics, it used to be that you could write down all the individual binary mergers and kind of study them individually. But now, again, kind of ensembles of these events are what we have to think about. So big data is one part of it. But I would say that a more core challenge of contemporary science is that both data and models, the data that we're trying to study, and the models that we're trying to do inference on, that they're both high dimensional. And traditional statistical inference is really good if you have a one-dimensional histogram. But the instant you're trying to deal with multi-dimensional data, multiple things that you're measuring at the same time, or models with a high number of degrees of freedom, then you're really in a situation where your ability to do visualization, both of your data space and model space, becomes very challenging. And so I would say it's more like a high dimensionality challenge. And in fact, coming back to the questions before about discrete versus continuous, that actually high dimensionality is also one of the big challenges. If you have discrete sample data in a high dimension, that's usually very sparse. And so trying to have a smooth interpolation over that is very challenging. And yet machine learning seems to be able to do a good job. So I would say that it's the high dimensionality challenge that we're trying to face. Now, it turns out that for the examples that I'll be using in these lectures, a lot of them will be collider focused. That collider data is actually not actually all that complicated by machine learning standards. I mean, yes, there's collisions every 25 nanoseconds, but a collision event, is something like, I don't know, 100 to 1,000 particles. Each particle is a vector in some 3 or 4 dimensional space. It's like not that big of a data. I mean, compare that to data sets that people are processing now, where you're doing machine learning on video data. I mean, that is a lot of information. And moreover, collider data has this advantage that it satisfies a certain property, that each individual collision is independent of all the other ones. And so even when we're talking about the data set of collider physics, it's like actually a relatively simple structure for that data set. So, I mean, not to say that our problems are easy, but compared to problems facing other areas of science or in society, actually, we have the advantage that our data sets are actually kind of better behaved than other areas where machine learning is having an impact. So let me just emphasize this point about why our data sets are simple, or simpler, at least for collider physics. So let phi represent phase space in general for some number of particles in any individual collision. And if I have n events, and if I want to understand the probability for getting those n events, so I have collision 1 that populates phase space, collision 2, and then up to collision n, that these collisions are independent of each other. So I can just talk about a product over probabilities, I from 1 to n, of the probability of each collision independently. So because I don't have to deal with those correlations, it's not like with video, where each frame of the video is conditioned on the one before it. Here, all the collision events are independent. And this is kind of a massive simplification, which, again, makes it relatively easy compared to other areas to apply machine learning. The other thing is that in terms of high dimensionality of our model space, the standard model is actually relatively simple. It only has 19 free parameters. If you start to think about the standard model as an effective field theory, and you look at SMEF coefficients, then okay, things start to get bigger. 10,000, 100,000, more depending on the flavor structure assumptions you make. The space, of course, of beyond the standard model scenarios is even vaster. You can think about combinatorially, how many different types of new particles could you introduce? What type of masses and interactions could you have? But actually, even in the space of beyond the standard model theories, you can oftentimes find simplification, such that you don't actually need all the information about a beyond the standard model scenario in order to build up kind of an approximate probability distribution. The real place where the explosion comes in, this is what makes things simple, or simple-ish. And then the thing that makes things hard, and I'm not going to even put ish on it, it's just hard, is that even though the kind of intrinsic dimensionality of something like the standard model is very small, what we have is we have many, many nuisance parameters that correspond to our ignorance about how you translate fundamental physics into an estimate about how the universe works. So, for example, we can do perturbative calculations using Feynman diagrams, but there's also non-perturbative physics. For example, the way that partons coalesce into hadrons, or the parton distribution functions, or the way that we model our detector apparatus. And this is where like the high dimensionality really starts to hit us. And this is where I view machine learning as actually something essential for our field to be able to tackle many, many more of things that are maybe not directly associated with the science we want to learn, but are necessary in order to make proper inferences about the universe. And let me just kind of show you what this looks like in equations, and we'll see some version of this later as well. So if I now want to go to like full experimental detector land, so this is now going to be the phase space of my experimental detector. Then in my paradigm of saying that I need to know the probability of my data given my model, okay, what do I have? I have the probability of seeing some experimental data. Well, thank goodness all the data is independent of each other, so I can just think about one collision event at a time. And then this is dependent on what? Well, it's dependent on theory parameters. These could be, for example, the standard model parameters. You know, I want to measure really accurately the Higgs boson mass, or the top quark mass, or the strong coupling constant. And then there are theory nuisance parameters using the symbol nu for nuisance. And these are things like, you know, I don't know fully my parton distribution functions, and those are things that I have to appropriately marginalize over. Or I have experimental nuisances. I don't know exactly the resolution of my experiment. So these are nuisance parameters. So even if the space that I'm trying to explore in theory land is relatively small, this could be very, very big. And moreover, if I really want to do a good job of modeling the probability of data given my underlying model, again, my model has theory parameters, nuisance parameters, might have other things that I care about, then as a theorist, what I can do is I can compute, let's say I'm a really awesome calculator, and I can compute in theory land the phase space associated with the fundamental particles that I'm trying to study. So this could be a theoretical generator. This could be a parton shower Monte Carlo generator. This could be an n-body simulation, conditioned on the theory parameters I care about and the nuisance parameters, which I'm afraid of. Like that's the land that I want to live in. I want to live in this world where I control, as a theorist, my calculation ability, and I'm the one who's responsible for coming up with the quantum probabilities that things are happening. Oh, but unfortunately, we also have our detector apparatus, which says, well, okay, you thought you made a 4-muon collision event. Well, the probability of that 4-muon collision event actually being reconstructed as 3, 4, or 5 muons, like that's some kind of transfer function. And then that depends on the nuisances of your experimental apparatus, and then you have to integrate over all of phase space. So this is captured, for example, by a detector simulation. And this just starts to become really, 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 really nasty. That is, even if I had beautiful theory, I still have to account for the fact that the data that I see goes through a detector. And this is the fundamental thing that I need to model. And this is the kind of the entry point for realizing why machine learning is so useful. So when I was a grad student and a postdoc, people would write equations like this, and they would talk about the matrix element method of actually really trying to model these things and do this integral and whatnot. It's very, very challenging, very, very computationally expensive. The reason why machine learning, in particular simulation-based inference, is so powerful is it essentially allows you to sidestep some of the challenges of trying to do this more direct approach. With, of course, all the caveats that come along with the fact that you're trying to do an analysis using a machine learning strategy that doesn't necessarily have access to all the information that you would need to make fully robust predictions. So why do you need simulation-based inference? Well, a couple of reasons. One is that this integral over phi is painful. The next is that your detector simulation, or for that matter, even your theory generator, are rarely known analytically. So, for example, I'm writing this thing as if it exists, but we actually very rarely have closed form expressions involving special functions for these things, and certainly not for a detector. And so if my goal is to try to find the model that best matches my data, and I'm imagining trying to vary these parameters around, well, if I don't have closed form analytic expressions, that optimization is extremely challenging. And the last is just what I said already, is that the parameter space is huge. And typically not directly differentiable. So when you're doing optimization, as I'll remind you in the next lecture, when you're doing optimization, you need to be able to take derivatives. Well, good luck taking a derivative of this beast. And while it would be absolutely amazing to rewrite all of the software frameworks that we use in fundamental physics, rewrite it in a way that's fully differentiable on a computer, that's not where we're in. And so part of the axis of the one direction of the centaur, which is that physicists need to learn to think like a machine. That is, we actually have to think about the computational structures that we're doing in order to make computationally efficient strategies to manipulate these objects. These objects in general, probability of data condition model, these are known as likelihoods. To manipulate the likelihood, that is the probability of data given a model. And machine learning is one strategy for doing that. Okay, so this is kind of a motivation of why actually you should think about. It's not pencil and paper calculations anymore in fundamental physics. Very few pencil and paper calculations exist anymore in theoretical physics, at least ones that are interesting. That we're getting to the point where computational strategies, whether you're dealing with theoretical data or experimental data, seems to be really important. And thinking about computational efficiency and thinking about computational strategies becomes really important for fundamental physics studies. Okay, so that's one direction. So that's the physicists need to learn to think like machine, and this has been something that I've been quite reluctant to embrace. I was trained as a pencil and paper theorist. I thought I could gain insights into the universe just through my head, and now I realize that indeed I have to code things up, and this is one of the reasons why you have to do it. This is a nice expression, but one that is kind of in practice useless unless I actually have a computational strategy for it. Okay. So we need to learn to think like a machine, but why does the machine need physics? Like, why can't I just export all of my data, hand it to someone who knows absolutely no physics, and just say, please discover the underlying laws of the universe? I mean, after all, we've encoded all of humanity's knowledge about physics into archive preprints. So why can't I just train a chatbot on all the things in the archive or in published works and just have the machine process all that? And maybe we actually will get to that point. But what is it that actually you need? Like, why do you need physics insights at all? Why not just translate all of our problems into a computational language? Why do you actually need to have physics knowledge? So, why do machines need to think like a physicist? So one example is just kind of historical in the sense that we've been doing a lot of physics before the machines came around, and so we know a lot about our problem already. In fact, I had a conversation with some engineers at Google a number of years ago, and they stopped our collaboration because they said, Jesse, you know too much about your problem already. And it's like, basically, I knew so much about the problem. I knew all the strategies we had tried that I'd already gone through my list, and my list was longer even than their list. And so, okay, that's when you've had a century of quantum mechanics to stare at, you actually gain a lot of intuition about what works and what doesn't work. So what's an example of something where if I use a blind machine learning approach, I wouldn't necessarily get like the optimal answer, even if I were to throw it at a machine. So a classic example is that having to do with symmetries. And you'll be hearing more about symmetries from Nathaniel later. So let's imagine I'm doing a collision at the LHC. I go into my detectors cylinder and I have a bunch of particles coming out. And then, again, the thing that I'm trying to do is I'm trying to figure out the probability of my data given my model. And because the protons at the LHC are unpolarized, that is, they don't have an intrinsic spin orientation, they're basically all uniformly sampled. If I do a rotation around, okay, so now I have capital phi and lowercase phi, so I do lowercase phi for the rotation around the beam pipe. I just know that the probability for seeing one phase space point and the probability for seeing any rotated version of that phase space point are just equal. So that's knowledge. Now, of course, you could generate that knowledge by getting more data. I could just generate more and more collisions, and that would explore the rotational direction. But that's not computationally efficient. It's more computationally efficient to imagine encoding the symmetry structure into this probability and telling the machine, look, if you're going to try to predict the probability of some phase space point, make sure that that prediction is the same, that the probability is the same if I do a rotation. So that's a classic example of where domain knowledge is relevant. We heard about Fermi doing work on fermions here in Florence, and of course we know that identical particles are indistinguishable. And so what you'd like to do if you're doing a study of bosons or fermions or even collider data, you'd like to make sure that the boson fermion structure is preserved. And this turns out to be a really kind of important domain knowledge that if you don't think about it, your machine learning architecture might not be aware of it. Okay, so we're going to be doing an example of this next time, very quickly, but an example of how can you account for information that you know about your data sets. I think I saw a hand up. Yes?
I don't want to be pessimistic here, but why is the machine learning cannot learn that? Like this thing, all these symmetries and rotations.
So,
Difficult for them and for us. Let's
good. So the question was, why couldn't the machine learn that that symmetry was present, right? So, yeah, why not? I mean, the lesson of my last lecture is that you should dream big. Come up with a computational strategy that, given a data set, will be able to approximate what, for example, the Lie algebra it is that describes that data set, and then does it in kind of iterative way of collecting more data to check its hypothesis about whether that symmetry is present or not. Like, why not? In fact, there are people who try to automatically learn the symmetry in a data set, and one of those people is standing in front of you. So yes, wouldn't that be amazing if I could actually like tell a machine, please, as part of your inference, please infer the underlying symmetry structure. But you have to do something to make that happen. Like machine learning algorithms just don't like run themselves. They're based on optimization. So what is the optimization in response to data such that the answer is, here is the Lie group that describes my data set? It's a fascinating question. In fact, it comes to like some really amazing facts about symmetries and symmetry breaking. So you can actually prove some certain things about naive ways of building neural networks to identify symmetries that they won't work because you need to account for the fact, like a physicist would say, you need to account for the order parameters that are present in the system. And so actually, like, it's not to say you can't do it, but you better build a machine learning algorithm that will have that as the outcome. But a naive use of machine learning classification or regression or generative modeling will not do that out of the box. You have to do additional work. But yeah, let's do that. Right? I mean, and that's a fun research project of which there's various people who have been trying to do that. I can tell you that one of my frustrations with that line of research from my own perspective is that oftentimes symmetries like this are only apparent in one coordinate system. So if I have a sphere, right, that's clearly symmetric, but if I look at a sphere in a funhouse mirror, it's not symmetric. And so then I say, oh no, I want to find under all deformations, I want to find some kind of rotational symmetry under all deformations. And then what you find is that everything's symmetric because it turns out that every single probability distribution up to topological obstructions can be mapped to a n-dimensional Gaussian. And so everything looks fully symmetric if right. So actually I only understood the definition of a symmetry by trying to do exactly what you were saying. Like, what does it really mean for something to be symmetric in a way that's coordinate independent? But yes, you could do it, but don't just say the machine will figure it out. You have to design the algorithm such that the output will be the thing that you want. Does that make sense? Yeah. And that's what we're going to do here. I'm going to just build an algorithm that has, well, that one's not a learning one, but where I just have the insight baked in. But you can, again, imagine it trying to be done as an inference. So, okay, this is some knowledge that we have. There's other things that we know about that appear, for example, in collider physics. If I go back to my lectures the last time I was here at GGI, a principle that's called factorization, which basically says that quantum probabilities break up into individual semi-classical pieces. That's something that you can imagine teaching machine learning algorithm about. Not all standard model parameters are relevant for every process you want to study, so you could figure out like what are the parameters that are most important for the things you care about. But the thing that I want to say is that domain knowledge from physics. So this is the jargon term. Domain. When people say I want to incorporate domain knowledge into machine learning, domain is your area. So for us, that's theoretical physics. You can inject this into machine learning systems, but it requires effort. You have to do something. It doesn't happen out of the box. Okay. I want to make one more statement. And this really kind of cuts to the heart of what was being asked about. Well, why can't the machine just figure it out? Um, so for me, the main reason to put physics intelligence and bake it into artificial intelligence is because of uncertainty quantification. So if you search up machine learning and uncertainty quantification, you'll find all sorts of papers about this. Okay, but at least restricting to particle physics, right? Particle physics we are a 5 sigma discovery field. And if you actually start to think about what does it mean to be a 5 sigma discovery field, it turns out there's very few machine learning tools that can claim that level of reliability. So a 5 sigma discovery field, what does that mean, roughly speaking? So we have the probability of my data, let's say, given my null hypothesis. Let's say I think the standard model is correct. And if I'm 5 sigma discovery and I see some data that looks a little bit weird, well, how weird is it? So what is 5 sigma, right? So 5 sigma is so 5 sigma. This is 1 in a few million. So if you really want to claim with just machine learning that you have said that your data is more anomalous than a 1 in a few million shot at happening, then you have to be able to effectively simulate the standard model and the LHC and all that stuff 1,000,000 times to check that whatever thing that you see didn't happen. And in the spirit of wanting to do things in a computationally efficient way, like to claim that it's not just a statistical fluctuation, you better be generating all that statistics. Or you need to use domain knowledge to help you understand the way that your data behaves such that you can extrapolate from much, much less data to be able to claim something like 5 sigma. And again, standard machine learning strategies have a very difficult time getting to that level of accuracy. There are actually machine learning strategies that are trying to really try to do this procedure of getting like perfectly calibrated n sigma intervals. But 5 sigma, that is daunting. So yes, you can throw data at the problem. You could simulate 1,000,000 reruns of the LHC for every choice of nuisance parameters that you care about. But in my mind, it's much better to take advantage of physics knowledge to do more efficient estimates of uncertainties. And the thing I want to say is that machine learning should make our results more reliable, not less. And so what we talk about machine learning, we worry about hallucinating AI chatbots, but that's in some sense the wrong framing. Machine learning allows you to tackle some of these challenges in high dimensional spaces and gives us a chance to actually really hit 5 sigma discovery understanding, even in the presence of many, many nuisance parameters or variations or big models. At least that's the dream. Okay, so that was my sales pitch for Centaur Science, that we need to, as physicists, learn to think more like a machine to come up with computational efficient strategies to realize our goals. But the flip side is that machine intelligence by itself doesn't by default understand things that physicists take for granted. And for things like uncertainty quantification, for things like symmetries, for things like factorized structures, these are things that we can take advantage of our physics knowledge and make them into our architectures. So let me pause to see if there's any questions before I move on. Okay. So There was a question before of could you teach the machine to learn asymmetry? So let's abstract that. Can you do X with machine learning for all X? And the answer is almost certainly yes. It may require some creativity. It's a research question. It may be very hard. Um, but oh, the real thing is, but is X scientifically sound? Okay. So, for example, something that has ended up on the cutting room floor for these lectures, which we could talk about it during Q&A. It's something that I care a lot about, but there's only finite amount of time this week. Is Lorentz equivariant neural networks? So we talked about rotational symmetry. Well, why not the full boosts and rotations of SO3, 1? Can you do it? Yes, you can. There's lots of papers on it. Do a Google search. You'll find a ton of them, including ones that I've written. So the question is not, can you do it? In fact, you can do it in many ways. But one of the questions that you'd have to say is this actually the right symmetry? Or how would you use it in a responsible way? So in particular, we're doing collisions at the LHC in a certain center of mass frame. The whole system is boost invariant. If I also boost the beams, but any individual subset of my detector is not boost invariant. One, because the detector itself lives in a particular preferred reference frame, but then also because unless I also Lorentz transform the incoming states of the scattering amplitude, then the actual final states themselves are not Lorentz invariant. So if you're going to use Lorentz symmetry, which is a great idea, you need to make sure that it's the right symmetry for the right type of problem. And if you are doing this with data that's been distorted by a detector, that may not be a good idea. So that's an example of something where you can do it. It's fun to do it. It's really fun to write that paper. And in certain cases, you can show it's useful. But if you just blindly apply it, it can lead you astray. And it can actually be worse than just doing regular machine learning without that additional domain knowledge, or what's known to as inductive bias. So physics intelligence, let me just write this down. So domain knowledge, another term that you'll hear people say, domain knowledge is related to something that's called inductive bias. This is a good kind of bias. This is the bias where you are affecting the decisions that you're making because of knowledge that you have about your domain.
Can I ask you something?
Yes.
So it seems from this discussion that the best use of machine learning is when I have a problem that I know very little about. Like if I know a lot about, and I want to like, I want to be very exclusive, for instance, in my detector, my collider search. It's like it's typically a bad idea unless I give him a lot of information, say.
So let me summarize the questions. You're saying it sounds like machine learning is best in cases where I have little knowledge, and if I have a lot of knowledge, then I should use existing tools.
Yeah.
Right. Yeah. And I would say actually, if you think about forefront challenges in our field, and you ask, can we, with current computational infrastructure, get to where we need to be? I am worried that our field is going to come to a standstill unless, even in cases where we know a lot about our problem, we don't do some machine learning aspect of it, because we're just going to hit computational walls. So like this is pretty clear in the case of something like lattice gauge theory. Like lattice gauge theory, you say, what's stopping us from, even putting aside the sign problem and whatnot, like what's stopping us from pushing the lattice to even more refined lattice volumes, or pushing us to go higher in the periodic table and actually study like higher Z or A nuclei? It's just raw computational efficiency. And if you don't have something like machine learning, we're never going to get there. Like I look at SMEFT, we were having a conversation at breakfast about this. Like SMEFT, like think about how hard we have worked to measure mu on g minus 2. That's one parameter. Or there's a debate about the strong coupling constant, one parameter. Okay, actually strong coupling constant is correlated with the top quark mass, might be correlated with the Higgs boson mass, but kind of 3 parameters, right? And how think about doing a full SMEFT fit and really like tackling the 50, 100, 1,000 dimensional space and really thinking that reliably we can know correlations between those parameters, all the nuisances that might affect that, right? And then you just start to get to a situation where even though it's like the opposite, it's like because we know so much about our field, we can actually take advantage of the fact that we have that knowledge to make sure we build machine learning systems that are reliable. So we know something about like interference structure of amplitudes, such that I basically know that what diagrams will interfere, what diagrams won't interfere. That tells me the scaling of the amplitudes as they change certain parameters. We actually know a lot, but tackling that huge space is extremely challenging. And so, yeah, you want to go back to the days of Markov chain Monte Carlo to sample your space, right? I mean, the Astro folks kind of very quickly realized that they couldn't sample that space efficiently, and that's machine learning has been like incredible for being able to open up those huge parameter spaces. And we need to make sure that we do the same thing. And it's taking advantage of more information. But, and this is maybe the point, take advantage of that information, but synthesize it with existing domain-specific tools. And so I'm not saying throw everything away. I'm saying use machine learning to make our results more reliable. Our current infrastructures make them more reliable, which seems, again, very, very, very doable. And in my view, absolutely essential. Again, because of this nuisance parameter issue and the 5 sigma requirement. So, okay, so what's another thing can you do? Can you train a foundation model to on simulated data to improve all machine learning tasks? Okay, well, it's a question of what improve means, but what a foundation model is that you have, roughly speaking, you have data comes in to some foundation model, and then you have some kind of auxiliary tasks that you're trying to make your machine learning solve. It might not even be a task that you care about. The one that you're probably most familiar with is with ChatGPT. ChatGPT, the auxiliary task that it's doing is to learn the next word in sentence sequences. So it's next word prediction. That's the task that you use to train this kind of foundation. But of course, we don't leverage ChatGPT just for next word prediction. It's turned into a query system or chatbot system. But you can nevertheless use this foundation model as trained on some auxiliary task and refine it for some other task. And there's various different strategies for refinement. Could you do this with particle physics data? Take a ton of data trained on some set of tasks, might not even be the task that you care about, and then just refine them for other things that you might want to do. Can you do it by this theorem? Yes, you can. Is it a good idea to do it? Because what this will do, this will certainly reduce the variance of your predictions. Yes, but it might, or might not, with a giant question mark, introduce biases in your answers. So can you do it? Yes, you can. Should you do it? I actually don't have a strong opinion about this, other than I don't understand actually how these systems work well enough to advocate for them. For people who are watching this in 2030, when foundation models have taken over everything and everything in particle physics is done with foundation models, remember I'm giving these lectures in 2026. And my apologies to my collaborators who are currently working on foundation models. This is not an attack on you. It's tough when these things are recorded, right? Because anything that you say will be used against you in the court of public opinion. Okay, so can you, for example, build a trigger for anomalous LHC events or anomalous time domain astrophysical events. Can you do that? Absolutely yes. And these are being developed by basically every experiment is looking at ways of flagging anomalous events. But yes, you can do it, but what's your definition of anomalous? And we'll talk about a little bit about that on Friday. But what do you think an anomaly is, and what algorithm do you want to use to define that? And this really starts to become a theory question. That is, can you do it? Yes, you can, but have you done the theory to think about whether it's a good idea, or even what the formal definition of what you're trying to do is? And then the most ridiculous thing that I can think of, train a generative model. So a generative model is a type of machine learning model that will generate synthetic data for you. So I talked about being able to simulate data. Typically, you want to simulate data with a physics simulation. But you can also have a generative model, which uses no physics knowledge, is just trained on examples in order to generate new synthetic data sets. So train a generative model to mimic the LHC. You choose some notion of statistical equivalence, and you say, look, this generative model has been tested to whatever accuracy that it statistically is indistinguishable by whatever statistical measure to the LHC data. And then toss the raw information. That is, like, delete the database with all the real data in it. So this sounds insane, right? This is saying you build an AI system to mimic your data set, and then you throw out the real thing. It sounds insane. And then you realize, wait, we're doing this already. We have trigger systems at colliders. We only can store a subset of our events. We're throwing out information already. Maybe we need to think about computational balance to say, well, what information do we throw out and what information do we keep? Could you imagine that the legacy of an experiment could be the generative model that mimics the data set? It's a little bit hard to imagine. So you can do it. But should you? And again, with this mantra that machine learning should make our results more reliable, not less, maybe that actually this is a way of recovering information that's being lost through traditional analysis strategies. So machine learning gives us an opportunity to dream big, and we should dream big. These lectures are not nearly ambitious enough from that perspective. So we're talking about simulation-based inference. Everything's going to be very well grounded. Simulation-based inference, optimal transport, like these things are pretty firmly established. I'm not going to be talking about, my fun late night conversations with Claude. Claude is both a fascinatingly flawed physicist and also a very good therapist. Though I would recommend going to the events on Wednesday. You're probably going to get more effective advice about mental well-being than you would get from an AI agent. What I like about simulation-based inference, in some respects also optimal transport, from a pedagogical perspective, is that the ingredients and the end goal is very clear. But I do think that the future of AI for fundamental physics will go dramatically beyond simulation-based inference. Okay, so there is no way I can talk about everything that's going on in the machine learning for fundamental physics space. But we can end at 45 minutes before the hour, or 15 minutes before the hour?
I think you have still 30 minutes.
I have 20, 30 minutes left, great. So I'm actually going to start on a little bit of lecture 2. But before I do that, I want to take this opportunity to just hear from you a bit. So this is my own curiosity of your topics of interest. Now, my lecture notes are already written, and I'm having too much fun doing my modular bootstrap equations. I'm like really close to like having some fun results, and so during the evening hours, or with an Aperol spritz, right? Like that's what I'm working on. So I'm not going to rewrite my lectures. I could, but maybe 5 minutes or so of something. So I'm curious. Are there things that you're hoping to get from these lectures? So it's just that I can then disappoint you, that I don't cover them. But I am curious. Of course, you came to GGI probably not for me. You came for the full set of amazing lectures. But I'm curious what you might hope to learn this week, and if I can do a slight nudge in that direction, I'd be well. I'm not going to do it, but I can pretend like I'm going to. So other topics that you were hoping to learn about? Yeah.
Kind of to what extent it's applicable for a theorist who does not like devote their time fully to machine learning to actually use topics from machine learning in their research.
I went.
Well, for example, like we use numerical differentiation
Yeah.
in Python, for example,
Yeah.
without being a computer scientist.
Yes.
Is machine learning at a point where I can now use some large network, some foundational models to actually improve my own research?
Okay. Good. So actually, this is something I can just address right now. So the question was, to what extent do you have to become an expert in using these tools, or are these tools more or less off the shelf? So another way of saying this is, so during my career, I forget what version of Mathematica I started with. Again, this has nothing to do with machine learning, but capabilities of Mathematica that have been added to the code over time. So the one I remember as a grad student was, how do you build, this is so stupid, like, how do you build plots that have error bars on it? And it turned out to be like really frustrating in like the old version of Mathematica. Now I'm doing Mathematica right now, and it's like, oh, do I have to figure out how to use the error bar package, which was always really buggy? Or no, it's been like baked in to listplot. You just like put data with error bars, super easy. Make asymmetric error bars, all the things that were painful. Like that was now a thing that had been introduced. And so that's a case of the community as a whole creating more easier to use. What? Yeah, yeah. And so machine learning is now at the point where there's a huge number of relatively easy to use packages. Some of them have been generated by my own students, and so you don't really have to know that much in order to start using these tools. The challenge that I see is that I see people curious about machine learning, taking off-the-shelf things and not really understanding how they're supposed to work or whatnot. But this is how you evolve as a field, and I myself am evolving. So what I'm doing right now, I'm developing a new optimization algorithm. Like this is like new version of gradient descent. That's insane for a theoretical physicist to be working on that problem. There are professionals who have been working on optimization forever. Why should I care about that particular detail? And the answer is, for most of my work in machine learning, I didn't need to get into the guts in that way. But I'm like hand coding in this in Mathematica for how you're doing a better version of gradient update. Why? Because my problem, I can't solve it using standard approaches. So the short version of the question is that, are things simple enough that you can just plug and play? Yes, as long as what you're doing is close enough to what other people have been doing. It just happens to be that in fundamental physics, we're almost always pushing against the domain, against the boundaries of something. And if you do decide to go into this area, you're going to find yourself hitting up into limitations. And you have to decide for yourself, like, how much do you want to work on addressing those limitations? And oftentimes, and I highly recommend this, and maybe Nathaniel could even speak more to this, is that it's really nice to have a collaborator who you can sit like across the table from, who knows a lot more about that aspect of machine learning than you do, and have them help you understand and have a conversation about that. And some of my most fun collaborations have been working with someone who has expertise on the more computational end of the spectrum. Though actually at the end of the day, it ends up being my grad students who do a lot of the coding, because it ends up being kind of physics-specific data types or assumptions. But those cross-disciplinary dialogues are really helpful. But as I was trying to say to Diego, I think it's inevitable for our field that we're going to have to go more in this direction. And if you prefer to just think about it, numerical optimization, don't want to use the words machine learning, please go ahead. computationally efficient strategies for processing large amounts of data, optimization response to data. You don't need the buzzwords of AI or ML for that. But if you want to get funding, sometimes helps to use. Yeah. So, did I address your question?
Yes.
Yeah, don't need to go on the bullet. So what other things are people interested to hear about? Blank slate.
Interested in understanding how reliable are the results of machine learning.
Uh-huh.
So you already mentioned genetic models, no?
Yeah.
At some point, we need to understand how reliable before we draw data. No? For example, at the least.
Yeah.
Introducing biases or the right biases.
Right. So if I'm efficient in my lectures for lecture 3, I have bonus. If you ask that question again and allow me to go a little bit over time, I can address this in the context of uncertainty quantification. So my basic philosophy these days is that don't talk about the reliability of ML as if it's like some static thing. Like thinking about machine learning as some static object that you deal with, like that's not how we think about reliability. Reliability is a more probabilistic thing where you say, I have a range of possible things that the machine learning might spit out. Within, I don't know, 68%, 95% of the outcomes, do they correspond to what I expected to? I have a more statistical notion of reliability. And so this is why I keep pushing on this nuisance parameter thing, is that nuisance parameters are saying reliability of machine learning results. Really what it's saying is, can the machine learning accommodate nuisance parameters in a way such that I can actually draw n sigma confidence intervals using it? And I can show you in the context of uncertainty quantification, one first approach in that direction, where I have provable guarantees about what's going to happen, though it is admittedly limited. But the zeroth order answer to the reliability of machine learning is that you can't think about it as just a binary, yes, it's reliable, no, it's not. It's a distribution of, like, at some level, there's like, if people have ever gone onto a chatbot and asked the identical question in separate windows and seeing the different answers that you get, it's the distribution of those answers that really is telling you about the reliability of the system, not any individual answer. And sometimes actually having a wide variety of answers, so that's a high variance, is actually a good thing, because if you have high variance, then that actually tells you something about the reliability. And if you refine the AI system to be to reduce the variance, then you might get a bias, or it might reduce the variance onto the wrong answer. And so actually, I like thinking about more inflating our uncertainties to capture the full variance of the possibilities. But on the third lecture, I might be able to say a little bit about this.
Extrapolating to non-perturbative results from perturbative answers, like finite diagrams.
Okay. So extrapolate from perturbative to non-perturbative physics. And the short answer is I will not say anything about that. I will say that the language of optimal transport, which I'll talk about on the fourth lecture, is one that at least gives me a number associated with, when I do this extrapolation from perturbative to non-perturbative, some guarantees about some other behavior. But I will not be talking about that. This is a fun thing for Q&A to think about. What does that even mean as a physics problem before you then throw machine learning at it? Other things that you want me to talk about? Hope that I talk about. Buzzwords that you've heard. Yes?
It would be nice to know more about the observables that you use to feed the machine learning model.
Okay. So observables used to train the machine learning. Okay. So the question is kind of what observables are some sense like kind of what auxiliary tasks to use to train the machine learning, and I'm not going to say that much about it because my current opinion is that you use all of it, which is not a very helpful statement. So I'll go in the other direction. I will be going in the kind of anti observables that you can put in histograms direction and advocate instead for unbinned full phase space things in the third lecture. But we can talk about that in Q&A. What have people done traditionally? You mentioned having bases of observables, and that's definitely something that one can do. And there's some interesting things that haven't been published yet that might change my mind about this. But my current view is actually saying that contrary to my best top cited papers, I am known, at least I'm cited on Inspire, because I've developed observables, and now I'm basically saying, actually, don't do that anymore. And so I've been fully assimilated by the AI to even toss out my own work, which is a little bit sad. But you'll see, well, okay, I won't have time. You'll see how some of it will come back in the optimal transport lecture. But partly I'm not going to talk about this because I actually don't think about summary statistics as being the best strategy for us to think about things right now. But again, this is 2026 in January, and I might change my mind. Yeah.
Maybe to know how this can be used in like abstract mathematics.
Ah.
Where there is no data that for coding theory, for example.
So I'm definitely not going to talk about that. But the answer to your question is that abstract mathematics is like the perfect context for this stuff, because we have super trustable generators of mathematically precise statements. Because you have automatic theorem proving software and languages like Lean that can generate arbitrary not arbitrary strings, definitely not arbitrary, strings that correspond to mathematically rigorous statements. And so you actually have a generator that can generate lots and lots of data. But like the challenge is like figuring out, well, what are the principles behind that? How do you figure out whether a mathematical statement is interesting or not? So I would say that that's actually a beautiful context for thinking about these ideas of what does it mean to come up with fundamental insights into mathematics. If I can generate for you true statements, but are they useful? Are they helpful? But I'm not going to say anything about that. But just want to say that that type of conceptual, well, it's not even conceptual. It's just strings that have an attachment to it saying, yes, this is mathematically valid. That's a fascinating, gigantic, infinite data set to explore, which I think is perfect for this type of machine learning work. And so we like to think about mathematics. We like to think about quantum field theory as like somehow this special, beautiful, elegant thing. But to the extent to which it's well defined and we have a symbolic expressions for what we're doing, it's actually perfectly well suited for certain types of machine learning strategies. Not the ones that I'm talking about here, but for other machine learning strategies. Yes?
How to know what input has the most influence on the output, so we have a more explainable model?
Yeah. So, okay, input, influence on output. So, and then you use the word explainability. So here, I probably should say something about that, but I'm not going to for reasons of time. But I actually don't like thinking about it as, well, sorry, actually, the way you said it was careful. You said, I want to know the influence of the input on the output. That is a scientifically rigorous statement that I can make. There's ways of quantifying that. There's like information theoretic concepts like mutual information that I can use to try to quantify that. There's other types of approaches that I can use. The thing that I don't like is this word explainability. Why is it that knowing the influence of the input on the output, why does that help you explain what the machine learning is doing? Like when we say that, like, are we sure that that's actually the question that we want? So I think the context that we often think about this is saying, I'm worried that my machine is taking advantage of information that I don't trust. And so if an input that I don't trust is affecting the output, that makes me worried. And that's the direction that I think is reasonable to ask it. But just saying, I would like to, in general, understand the machine learning by understanding input-output relations. It's like, but for what purpose? As we'll talk about, machine learning is just some optimization algorithm. We don't usually ask of functions like, tell me the correlation between the input and the output, and saying that helps me understand the function. Like, I don't understand the sine function better by understanding the input and the output of the sine function, and that doesn't give me explainability of how the sine function operates. But I think the point is more about kind of reliability, and that if I'm going to try to get some kind of explainability, I, as the human operator, need to define what I mean for something to be explainable. And this is the key thing, let's say the outcome is one that you don't like. You're like, ooh, I'm really worried the machine learning is taking advantage of this information that I don't trust. Then tell me what you're going to do about it. How would you change your scientific conclusion based on the result of some explainability, interpretability algorithm? And that's where I think we don't spend enough time thinking about it. That we check for explainability, interpretability, but then we don't say, well, how I'm going to respond if it doesn't work out the way that I want to. And so I think the language that I like better is the language of robust machine learning, of which explainability can be part of that. But you can have a system that is completely black box, no idea what it's doing, 100% robust because I can understand it at the 5 sigma level, even though I as a human cannot process it because it's living in some giant high dimensional space. But I can check it by running pseudo experiments and I can convince myself that it's reliable. So explainability and reliability are not necessarily the same thing. I can have reliable things that I can't explain and explainable things that are not reliable. So that was soapbox there. Yeah. Yeah.
Related to the last question.
Yeah.
How to do prompt engineering this?
Oh, how to do prompt engineering. Okay. So right. So we are not going to be talking about chatbots at all. But I can tell you from my own personal experience that it's incredibly maddening to me that I don't know how to do this in a way where I can elicit the kind of response that I want from a chatbot in a repeatable way. These are incredible tools, but for example, I've had. So I don't know if anyone's used Claude, but Claude is overeager to generate code for you. And overeager to generalize. And so I'm studying conformal field theories, two-dimensional conformal field theories, and I said, hey, Claude, could you help me come up with a list of all known conformal field theories with a certain value of central charge? And then, but maybe can you just start with one so I can see what your output format is? And so it gave me one, and I said, okay, that's great. So now, like, I want to explore the space. Can you give me some sense of what the space looks like? And then it just started churning for minutes because it generated a gigantic PDF file of all the information that it thought it knew about two-dimensional conformal field theories, of which immediately I could just check, because you just check in the literature, immediately it had hallucinated a particular partition function for one theory. It was wrong. It wasn't modularly invariant. It's like, well, you generated for me a huge amount of garbage and you didn't let me inject myself into it. Now, this is the particular version that is being used right now. So I wish I knew how to do that, how to use these systems more effectively. And so I look forward to go back to IFI to ask Matt Schwartz what he did when he was able to get Claude to actually generate something that he posted onto the archive. Like, what did you actually do for that? Because I myself have been frustrated about not having the level of control that I would like to have for these things. And it's been a very iterative and human brain intensive exercise of having that dialogue. Yes?
So actually, from these algorithms as a unit, for example, but with some abstract jack tagger, I might necessarily have but I don't necessarily know like what physically differentiates something from them. So how to extract that physical knowledge from the jack tagger.
Right. So, so the question is, given an giving a concrete numerical algorithm, how do I convert that into something with physics knowledge? I view this actually very similar to the case of learning symmetries. So, in the sense of, well, what do you mean? What is the definition of physics knowledge? And it's not very satisfying to say, I know it when I see it. So I'm talking to a reporter right now. Not right now. An email exchange with a reporter who's trying to understand interpretability in the sense of, given an algorithm, have I ever been able to reverse engineer the physics behind it? And I have some good examples. And then then you say, well, what did you do generically? How do you define that as a workflow? I say, I don't know, because I just, as a human, I looked at the AI output. I had some explainability layer in my algorithm. I looked at that explainability layer and I said, ah, yes, now I see it. But what was I actually doing? How do you algorithmatize that? And so I don't have a good generic answer for that. But it does seem to be important that if your goal is to learn physics, and you have some notion of what it means to learn physics, that is, is it a symbolic expression that's of a certain length? Is it a ability to translate to some other domain? Like whatever that definition that you have of what success looks like, can you have an algorithm do that? So I would love to know the answer to this question. But in generality, the examples that I have from my own research are ones where it really was the centaur approach. Like, I couldn't have done it fully from the machine learning side. I needed to have my domain knowledge. I needed to have a dialogue between the more computational and the more QFT part of my brains in order to figure things out. I don't know how to do it in generality, but again, it's a similar thing of, well, what does it mean to find a symmetry? What does it mean to have something that's physically interpretable? Yeah. Okay, any last questions that I won't answer before? Oh, we've gone through the hour, so I don't have to go on to lecture 2. But other things on your mind or questions? Yeah.
Maybe there's some physics-inspired optimization algorithms. See that it's possible to do a similarity between neural networks and backend networks.
So neural networks, yeah. So physically inspired optimization strategies. Sorry, say it again.
Other maybe than gradient descent.
Oh, other than gradient descent. Okay. So I'll explain gradient descent. So I'm not going to do this, not because I don't care about it. I'm working on it. I have actually more than one project in this direction. All I'm going to do, and we'll end with this, okay, because this is now the lead into the lecture tomorrow. So the lecture tomorrow is saying machine learning jargon, you can translate that to physics jargon in many cases, and that your physics intuition should guide the way that you think about machine learning. So let me show you why gradient descent is stupid using a theoretical physicist's logic, okay? So I have a parameter. Let's use generically B for the parameter. And I'm now going to update B. B will go to B, and then I'm going to respond by the gradient of my loss function with respect to B. And the coefficient I put in front of here is called the learning rate. So this is gradient descent. And this is manifestly stupid. Okay? Now, it happens to be the workhorse of like, I mean, this and its variants are the workhorse of machine learning optimization. But like, as written here, it's really stupid. So why is it really stupid from a physics perspective? And why does this give us an invitation to actually come up with better algorithms? So, so if we have a parameter, let's imagine that this parameter is actually like a coordinate in some geometric space. So we're going to translate this into a general relativity type language. So I'm going to put an index on my parameter. Okay. And then I'm shifting a parameter by its gradient, and the gradient itself has a lower index. So I have a, sorry, which is covariant, which is contravariant? This is contravariant, that's covariant? What, okay, which way it is. Anyway, again, the problems of being recorded. Okay, I have a contravariant vector that's being shifted by a covariant vector. That's clearly idiotic. Clearly what you want to do, clearly, is that this learning rate should in fact be, I mean, we're using the same symbol eta already. I mean, you might as well just, do that, right? That's clearly the thing that you should do from a physics geometric perspective. Like, just by dimensional analysis, ignore the upper lower indices, like a parameter in meters, like shifting by inverse meters, like just dimensionally it's wrong, right? So then you ask a couple of questions. So one, you can ask the question, well, do machine learning people know this? Of course they know this. They know this because this thing, which there's plenty of papers that talk about trying to have this metric, but if I have n parameters here, then this metric is n by n, And like neural networks these days, million, billion parameters, right? Like driving this thing is a pain. But of course, people know that there is computationally efficient ways of computing this thing, but then it's a memory issue, yada, yada. Okay. So um, this is an example of this need to have this centaur science. If you from the physics perspective, it's clear that you should have something like a metric that tells you how you move. But computationally, it's very expensive to compute this object or estimate that object. And what we do right now is that we do strategies to try to normalize our parameters. So if anyone's ever done machine learning and you've encountered the layer norm operation, the layer norm operation is an operation that's trying to, okay, I'm not sure that this is 100% true, but in my brain, what I think it's doing is it's trying to make this metric close to being diagonal, or at least having order one entries in it. So we have the thing of what you should do versus what's computationally efficient. And when these things are in tension, we need to find the right harmony. And so the thing that I'm working on right now is an answer to this question of how do you estimate this thing in a way that's not computationally ridiculous, that benefits from physics knowledge, but also runs in finite time in my goofy Mathematica implementation of it. But physics-inspired optimization strategies, like this is why you need one. And then you can look at this and now you can compare to the machine learning literature. And the machine learning literature has very smart people who are working on this stuff. And people have been working on optimization for decades. And there's like different strategies for trying to estimate this object. You try to like think about how many computational steps you need to get improved updates of that. So there's plenty of things in the literature already, but it benefits from some. I think it will benefit from additional physics insights. And this is just one example of a type of optimization where it's kind of obvious that it's not the right thing to do. And yet coming up with something better is not so easy because you are computationally limited and you have to think about this running in finite time on your computer. Yeah. But I ask me back in a year and I can tell you examples of that. Okay, so thank you all for your engagement in these lectures. Please keep your questions coming. The next time we will dive into machine learning through the lens of physics and do more equations on the board. At this point, we will adjourn for lunch, and then after lunch, Nathaniel will tell you all about beyond the TIFF paradigm. Thanks, everyone.